Finite difference and interpolation. Concept of derivatives is applicable for continuum of data. In many real-life problems, we come across data which are discrete in nature or discontinuous in nature. To solve such problems, we may use the concept of finite differences which are discrete equivalent of concept of derivatives. Finite difference approximations for derivatives can even be used to solve differential equations. Suppose you tabulate the observed data recording the input values xi which lie within the range interval AB and correspondingly the output values, and if you wish to estimate an output value for xi which lie within the observed range interval AB, that process is known as interpolation. When you estimate outcome or output for input values beyond the range of observed data, that process is known as extrapolation. Let us discuss the working of forward difference operator, which is notated using symbol delta or a small triangle. Consider function y equals f of x, where input values x are termed as arguments and output values f of x or y values are termed as entries. We have difference between consecutive x values as h, which is known as the interval of differencing. This is the general form of forward difference table. We record the input values x and the corresponding output values y. First forward difference is represented using delta y. Delta y naught equals y1 minus y naught. It has to be written in midway between values y1 and y naught. Delta y1 equals y2 minus y1 and it has to be written in midway between values y2 and y1. Delta y2 equals y3 minus y2 and so on. In general, we have delta yn equals yn plus 1 minus yn. Second forward difference is notated using delta square y. Delta square y naught equals delta y1 minus delta y naught. Delta square y1 equals delta y2 minus delta y1. Delta square y2 equals delta y3 minus delta y2. Delta square y naught is written in midway between delta y1 and delta y naught. Delta square y1 is similarly written in midway between delta y2 and delta y1 and so on. Third forward difference, delta cube y. Delta cube y naught equals delta square y1 minus delta square y naught, and it is written in midway between these two values. Delta cube y1 equals delta square y2 minus delta square y1, and this is written in midway between these two values and so on. Y naught is known as leading entry. Delta y naught, delta square y naught, delta cube y naught, etc. are known as leading differences. This representation gives us the working of forward difference operator. Delta f of x equals f of x plus h minus f of x. Here, first we take the output of function at the incremented position x plus h. From this value, we subtract the original value f of x. Properties of forward difference operator. Forward difference operator applied on a constant equals 0. Forward difference operator applied on constant times a function f of x equals constant times forward difference operator applied on function f of x. This is known as linearity property of forward difference operator. Similarly, you can write this forward difference operator applied on constant times f of x plus another constant times g of x equals a into delta f of x plus b into delta g of x, where a and b are constants. Similar to the product rule of derivatives, we have forward difference applied on product of functions f of x into g of x equals f of x plus h into forward difference applied on g of x plus g of x into forward difference applied on f of x. Similar to the quotient rule for derivatives, we have rule for forward difference operator given by forward difference operator applied on f of x upon g of x equals g of x into forward difference operator applied on f of x minus f of x into forward difference operator applied on g of x upon g of x plus h into g of x. Note that these two properties are slightly different from the quotient rule and product rule. We have for forward difference applied on product of functions, f of x plus h is multiplied to forward difference applied on g of x plus g of x into forward difference applied on f of x. The first function to which forward difference operator is not applied is incremented here, which is different from the product rule. Instead of square of denominator function appearing in the quotient rule, we are having for forward difference operator, the denominator function is g of x plus h into g of x. Another property, delta raised to m into delta raised to n applied on f of x equals delta raised to m plus n applied on f of x. Delta raised to n is forward difference operator of order n. Similarly, delta raised to m is forward difference operator of order m. Delta raised to n applies on f of x means delta forward difference operator applies on f of x n times.